world of aerospace right now, which is a mission by NASA known by the Mars Science Laboratory, and this mission is solely based on a rover or robot on the planet Mars right now, and the rover is known as the Curiosity. If you guys want to note down, my student ID is 011627. Okay, so at first I'll start to give you a little bit of introduction about what exactly this mission is all about. We will look into its entry, descent and landing, its EDL system, the risk analysis of what happens if the landing goes wrong. And I will conclude by telling you a little bit more about the mission. So let's start with the Curiosity. Curiosity, this rover that you see in this picture, is quite frankly everything that you need to analyze a planet. It can do anything that you think of. It can get itself out of any position. It can picture 360 degrees. It can portrait itself. It can drill through any type of rock, and it can extract the sample and analyze the sample and send the results down to Earth. The specifications. What was this rover all about? This rover was 900 kilograms of mass. That is 3 times heavier than any other object that we have landed on the planet Mars. And it enters the atmosphere of Mars at a speed of about 5,800 meters per second. If you're not familiar with that speed, that's about 21,000 kilometers per hour. I'm sure all of us either drive here or have been in a car. A typical car goes at about 120 kilometers per hour, right, in highway. This is 21,000 kilometers per hour. That's how fast it is. And it needs to stop from this speed in just 6 minutes and a half without a pilot aboard. So making the rover wasn't the big problem in this mission. The landing of the rover was the biggest problem. As I said, it's very heavy. Another problem is the distance of Mars to Earth. At the time of landing, the signal itself takes 7 minutes just to reach the Earth. So by the time that we get the signal that something is happening, that has happened 7 minutes before. So we have no control over what's going on right now. So that's why a completely automated system needed to be devised. So let's look at some of the landing options. First one is using airbags. Wrap this rover within an airbag and drop it down to the surface. This is not going to work for the rover, for this rover especially, because of the mass. The airbags cannot hold this mass, and the airbags will implode. So let's look at the second option, which is using retro rockets, jet rockets, to completely stop the spacecraft down. Using the jet rockets while it's descending, decelerating it down to the surface. But this one also doesn't work, simply because the propulsion from this retro rockets rises a lot of dust from the surface. That dust can damage the instruments of the rover. Well, we don't want the 3 billion rover to be damaged on the landing, right? So let's look at the proposed solution for the landing. Using the retro rockets, but instead of landing it all the way, we use something that we know as a sky crane to lower the rover down to the surface and keeping the retro rockets well above the surface, and we have the rover down on the surface. As soon as it touches down, the strings break away and the spacecraft flies away. So let's look at this entry, descent, and landing in more details. Here we have the entry interface at 5,800 meters per second. Now, atmosphere of Mars has air in it, has carbon dioxide. Air causes air resistance, which is a frictional force, and it slows the craft down by 92% to about 470 meters per second. This is a much more manageable speed, but unfortunately, this speed is still faster than the speed of sound. We cannot possibly with that speed. So we use the parachutes, the largest supersonic parachutes that we have ever used to land an object on Mars. 12 meters in diameter were these parachutes. But the atmosphere of Mars is quite thin. So it only slows the craft down to about 100 meters per second. So what do we do next? As I said, we use the retro rockets. The retro rockets are employed, and as we get closer down to the surface, we use the sky crane a set of 4 strings, each of them 9 meters, used to lower the rover down to the surface, and as soon as we have the touchdown, the strings break away, and this retro pack will fly away. So, what if it all happened as we expected, and what if it didn't? That's what we believe killed the dinosaurs, right? So let's look at it in more details. Here I use something that I like to call as an impactometer, which is quite frankly a force profile. On the vertical axis we have force, and on the horizontal axis we have time. So if you're not familiar with this, I'm sure everybody here is, the higher the graph goes, the more force the rover feels, so the landing is no good. Here we have the force profile for crash down as well as touchdown. You cannot see the touchdown. And the simple reason is that you have to zoom along this axis for 500,000 times before you can see the graph of touchdown. That is the difference between the force of a possible crash down and the actual touchdown. The crash down goes all the way up, and touchdown we have to zoom in just to see that graph. And just for your information, the area under these 2 graphs are equal because the change in momentum is equal. So, I pretty much showed you a whole bunch of graphs and all, but I think nothing better than a video can demonstrate this landing system. So ladies and gentlemen, the 7 minutes of thorough video. At this point, the spacecraft is inside the atmosphere of Mars, getting decelerated by the air resistance. Here we have the parachutes deployed. Now at this point, the radars of the rover is taking the exact measurement of what the altitude is and where it is, because the rover has a very precise position of landing in the Gale crater on Mars. So these retro rockets, apart from decelerating it, they actually take the rover to this precise position of landing. And here we have the sky crane being deployed. And let me show you this footage from the mission control during the actual landing last August. That is not a movie. Those are the engineers and the scientists who worked on this project for many years prior to this landing. And I'll tell you, this was one of the noble works of engineering and one of the most innovative things that human has ever done in field of electronics and mechanical especially. Here are some of the references and the sources that I used to put this presentation together, especially the JPL, Jet Propulsion Laboratory website, and the NASA website, and a paper that I read on the Mars Science Laboratory Entry, Descent, and Landing. Alright, thank you so much for your time. This is the end of the presentation. We will have a short Q&A session. Thank you. And if we couldn't answer your questions, please feel free to drop me an email. I'll get back to you.
Ali, what's the strength of Martian gravity?
Strength of Martian gravity is about 34% of the gravity of Earth.
Okay. Thanks.
So if it's 34% more, shouldn't you take precautions about that also? Because then the mass will be more on Mars.
No, not 34% more, it's 34% of
less.
Oh, it's 34% less.
Oh,
Okay.
That is actually taken into account because mass is constant. It's the weight
It's the
that
weight that
differs.
will matter.
So the downward force is different. So the figures that I used to come up with that force profile was actually according to the weight of the object on Mars.
On Mars.
So the delay in signal transmission, is it a two-way delay or just a one-way delay?
The 7 minutes is a one-way delay during the landing time. The delay can actually vary from 6 minutes to 15 minutes, depending on the position of Earth and Mars in space, because as you know, they're moving in orbits and they have different orbital speeds. So the time, the distance is actually not constant all the time. And time that was chosen for the landing, the delay was 7 minutes just to reach the Earth, and 7 minutes to get back to Mars.
Yeah, so I asked, is it a one-way or two-way delay?
7 minutes is a one-way delay.
The one way. So why sending signal to Mars? There is no delay.
There is.
Then it's a two-way delay.
The 7 minutes is a one-way delay. So the two-way delay will be 14 minutes.
I didn't ask with regard to the minutes. I just asked with delay. Is it a two-way?
It's a two-way delay.
So if it is a two-way delay, that means before you notice what is happening, it has already happened. So how do you communicate?
We cannot. Everything needs to be automated. For the landing, first, it gets closer to Mars. And then it has a very precise entry angle. Because if it gets very deep, you know, if it's very shallow, it will bounce off the atmosphere of Mars. Just like a rock, you know, what is it called? When you throw the rock on the surface of water, it just skips the rock, right? Now, it will be just the same thing off the atmosphere of Mars if it's very shallow. And if it's very, the angle is more than what it should be, more than the critical angle, it will burn in the atmosphere because of air resistance. Because as you know, air resistance causes heat. And if the heat gets over a certain limit, it will burn the rover. So it has a very precise entry angle. And before entering the atmosphere, there will be a small burn to put it inside the entry angle. And after it gets in, everything is automated based on the gravity.
So whatever the Curiosity does on Mars is not being controlled by man.
It is being controlled with delay. For example, like here we give it the instruction to start the drilling, and the drilling will actually happen 7 minutes later. And that is again based on the timeline. Now it's about 10 minutes time delay at this point of time. Are there any? I hope that answered your question. Are there any other questions?
Yeah. You said if there's wind, if it touches down, if the sky, what's the jetpack you use?
Retro rockets. Yeah.
The retro rockets. If you just use them, there'll be a lot of wind and sand blowing, and that will damage the rover's material. So, what about when it lands? And for example, it lands perfectly, and there's a sandstorm in Mars. Will that damage
Yes, it
the
will.
Mars?
Yes.
So then, the best time to then how will you know when to send the Curiosity to Mars? By measuring
we
the.
can predict something because at this point of time there are 3 satellites all orbiting the Mars that transmit data to Earth. So we can somehow predict how the weather will be, but there is never a guarantee about the weather on Mars. As you know, in 1978, Mars 2 landed. The rover Mars 2, actually it was a lander. It landed on Mars and it only transmitted for 20 seconds. And after that it died. And we never know why, because it never transmitted anything. It just transmitted a weird picture that was never described, never could be understood. And they predict it was because of the sandstorm at that time, but we never know. So there's a slight chance we have to take.
I think that would be.
Alright, thank you guys.